But again, this has to be normalized to be a unit vector so that we can take advantage of the Q matrix being an orthogonal matrix. If the columns of Q are not unit vectors, then this is not going to be an orthogonal matrix when we define it. So for our own convenience, we divide by square root of 2 to make it a unit vector. Now, I could have put instead of having the -1 here, I could have put it down there. Everything would work out the same way. There's a choice in that regard. Okay? Okay, so now I have my Q matrix is going to be just these two columns stacked side by side. And so what I've shown is that if all the calculations are right, so my lambda matrix is this, and it's lambda 1, lambda 2 on the diagonal. My Q matrix is, has this as columns, so 1 over square root of 2, 1 over square root of 2, and then -1 over square root of 2, 1 over square root of 2. And then my Q transpose is just the transpose of that matrix. So it just looks like this. And if you multiply these three matrices together, you should reproduce that matrix. Okay? Any questions about that? Okay, well, let's use this then to calculate the exponential of A. Well, exponential of A is just going to be the Q's stay the same. The Q and Q transpose stay the same. And in the middle, we exponentiate this, so we get e to the 1 is e, 0, 0, and e to the third power. And then you multiply those three matrices together, and you have the exponential of A. Okay? Now, if you want, I can do it, but it's not very instructive. The only thing that it would be instructive to show is that when you do that, when you multiply these three matrices together, you do not get e to the 2, e to the -1, e to the -1, e to the 2. Okay? It will not be that. You do not exponentiate the entries of the matrix to get the matrix exponential. You do this. Okay? Now, we can also ask what is A to the 1/2 power. And that is going to be 1 over square root of 2, 1 over square root of 2, -1 over square root of 2, 1 over square root of 2. Likewise, the Q transpose is going to be the same over here as in the original matrix. And what are we going to do? What are we going to fill in over here? Volunteers. What goes in the middle for A to the 1/2 power?
Root 1 over 3.
Okay, so the square root of 1 is 1, the square root of 3 is the square root of 3. Okay, so that's when then you multiply these three matrices out, and that gives you the square root of the matrix A. And that matrix, when multiplied by itself, will give you A back. Okay? Okay, so what is all this good for? Well, let's go back to our problem, mx double dot plus kx is equal to 0. Well, this one right here. So this is a good example to keep. So we'll work out the general theory, and then we'll apply it to this problem. So the general theory says if I have mx double dot plus kx is equal to 0, then I'm going to make two changes of variables. Okay? So x was good, you know. X is good for formulating the problem, because you can see this is x1 and this is x2. But x is not so good when you go to solve the problem. But there are better coordinates to solve the problem. So what are those better coordinates? Well, what we're going to do is we're going to remember that here m is symmetric and k is symmetric. So they can both be decomposed in the way that I just did. By the way, before I do this, you may wonder if you can do all of this for matrices that are not symmetric. And the answer is sometimes you can and sometimes you can't. The important condition for being able to take square roots and calculate these matrix functions in the way that I did is that you have to be able to decompose S like this. So in other words, in all of this, the fact that the matrix Q and Q transpose were orthogonal was convenient, but more generally you can write a similarity transformation. But you can't do this for every matrix. You can only do this for matrices that, I mean, it's a technical condition, that all of the Jordan blocks are one-dimensional, okay? And what does that mean? If I give you a matrix that looks like 1, lambda, 0, 1, okay? This is a matrix where the square root does not exist. Particularly if, let me see, no, I think I have that backwards. Lambda 1, lambda, okay? So for example, if lambda is equal to 0. So the matrix 0, 1, 0, 0. There is no matrix that exists that when you multiply that matrix times itself, you get this matrix. Okay? It just doesn't exist. So it is possible to find matrices that don't have square roots, but symmetric matrices with positive eigenvalues always have square roots. Okay? Okay, so this is important for what we're going to be doing over here. So we're going to define new coordinates. We're going to say let y be m to the 1/2 power times x. Okay, so here x and y can depend on time, but m and k are constant matrices. Now if this is true, then y double dot, I take two time derivatives, they both pass through the m because it's constant, is equal to m to the 1/2 times x double dot. Okay? Now, the reason why that's useful is because over here, m I can write as m to the 1/2 times m to the 1/2. And so I can take one of these m to the 1/2 powers, that's multiplying x double dot, and I can replace that with a y double dot. So I get an m to the 1/2 times a y double dot for the first term, plus k times x. But it doesn't make sense to have y's and x's in the same equation, where if this is true over here, then what that means is if I take the inverse of this, m to the 1/2 inverse times y is equal to x. Now there's an interesting thing that happens if you look at the 1/2 power of a matrix, and if you look at the inverse of a matrix, A inverse is Q lambda inverse Q transpose. Lambda inverse is lambda to the 1 to the negative 1 power down to lambda n to the negative 1 power. Okay? Or if you prefer, 1 divided by lambda I on the ith diagonal term. Well, it turns out if you take the inverse of the square root of a matrix, that's the same as putting a lambda to the negative 1/2 power on the diagonal rather than a lambda to the positive 1/2 power. So to make a long story short, the half power matrix inverse is actually the same as the inverse matrix to the half power is the same as saying m to the negative 1/2 power. Those three things are all the same. And that's convenient because over here we can write this as m to the negative 1/2 power times y is equal to 0. And then we can pre-multiply everything on the left here by m to the negative 1/2 power. And that's going to cancel with this. So I'm going to multiply by m to the negative 1/2 power everything over here. Of course, when I multiply 0 by that, I'm still going to get the 0 vector. And so this is going to cancel with this. It's just going to give me, say, the identity matrix times y double dot. And then over here, this is going to be m to the negative 1/2 power k m to the negative 1/2 power times y is equal to 0. Now it turns out that this matrix right here is symmetric. So why is that symmetric? And that's actually the whole reason why I did this change of coordinates. If I give you, well, first of all, m is a symmetric matrix, right? And if I take the square root of m, I get a symmetric matrix. If I take the inverse of m, I get a symmetric matrix. So this thing right here is symmetric. This was already symmetric, and this is symmetric. And this is not only symmetric, but it's the same matrix as this. So if I tell you that C is a symmetric matrix, A is a symmetric matrix, right? Each of these is symmetric matrix. And if I take the transpose of this, what do I get? Well, by the transpose rule, the transpose of this is going to be C transpose, A transpose, C transpose. So in other words, the transpose of this matrix is equal to itself. So it's a symmetric matrix. So this matrix right here, if we call it the matrix A, is equal to its own transpose. So that's symmetric. Okay? Well, now we're going to make a second change of coordinates then. So I'll just rewrite what I have over there. Up here, it's the identity times y double dot plus A, where A is a symmetric matrix, times y is equal to 0. So what happened? By changing coordinates, I completely got rid of this matrix that was coupling the y double dots. So this is completely diagonal. If I can diagonalize this one also, then I will have completely decoupled my equations in a new coordinate system where I can just solve scalar equations. Since I know if I have a zi double dot plus, say, lambda I zi is equal to 0, this is the kind of equation that they teach you how to solve in your, sophomore level ordinary differential equations class. In fact, the solution to this equation is zi at time t is equal to some constant c1 times cosine of the square root of lambda I t plus c2 sine of the square root of lambda I t, right? So we all know about that. So if we can somehow construct a z so that each component of z has an equation that looks like this, then we know how to solve it. Okay? So here, z, what is z? Well, what we're going to do is we're going to decompose A into Q lambda Q transpose. And then what we're going to do is we're going to define new coordinates, z, to be Q transpose times y. And because we have a Q transpose here multiplying a y, that's going to be z. And so what is equivalent to this is we're saying that y is equal to Q times z. And if y is equal to Q times z and Q is constant, that means that y double dot is Q times z double dot. I've taken two derivatives and with respect to time, and each one passed through the constant matrix Q. So if we come back to this equation up here, we have, if we substitute this in up here, we have a Q z double dot. In fact, I can do away with the identity matrix. That's just there as a placeholder. Plus, and then this is going to be Q lambda times z is equal to 0. And then I can pre-multiply by Q transpose. Q transpose times Q is the identity. Q transpose times Q, this disappears. And so this right here is a vector equation where each component of this equation is simply this. Okay, so we've completely decoupled the coordinates. Now, in general, you can't just look at a problem in advance and say, I'm going to choose my generalized coordinates to be z1 and z2 so that my equations of motion will be diagonal. Okay? In general, you can't do that. Although in some specific cases you can, and we'll get back to that in a minute. But in general, you introduce coordinates, you write your equations of motion, and then after the fact, you diagonalize the system so that you can actually solve it. Okay? So, so let's go back to this system. And let's say that I give you initial conditions, x1 at time 0, x2 at time 0, x1 dot at time 0, x2 dot at time 0 are all given. So if I give you these initial conditions and I give you this differential equation, then the solution exists for all time greater than 0, and it's specified by the combination of the equation and the initial conditions. So let's use this methodology for this example. And actually, in this case, it's very easy. We can just divide everything by m to begin with. So I don't need to do the step where I took the square root of m. So this is an easier case than the general one. In the general case, this matrix would not be a multiple of the identity matrix. But in this case, it was. So I can just divide through by the scalar m. And this matrix is still symmetric, right? But when I divide, if I divide through by m, I'm dividing every entry in the matrix by m. Okay? That didn't alter the symmetry. Now, if this were m1 and m2, I could not do that. If these were two different values of mass, I couldn't just divide through. I would have to do this m to the 1/2 business that I started out with. Okay? Okay, so, well, in every term here we have a k over m. I could bring the k over m out front, and we can use what we know already about the eigenvalues and eigenvectors of this matrix that we just calculated. So, in fact, we can say that this matrix right here is K over M times the A, which I solved previously, right? Which was, so this is K over M. The Q was 1 over square root of 2, 1 over square root of 2, like this, I think, right? Or where did I have the negative 1? Was it up there? We'll be consistent. Was it up here or down here? Like this? Okay. So then we had a 1, 0, 0, 3, 1 over square root of 2, negative 1 over square root of 2, 1 over square root of 2, like this. So, in fact, what I can do is I can take this K over M, I can put it in the middle over here. Okay? So, so if I go through my formulation here, I can get my solution in terms of z's, right? Because the solution just looks like this. In fact, we can put more structure to this. If I tell you what zi at time 0 is and zi dot at time 0 is, we can solve for what C1 and C2 are. In fact, C1 will be zi at time 0, and C2 will be zi dot at time 0 divided by the square root of lambda I. And if you don't believe me, all you have to do is evaluate the left side at t equals 0. When t equals 0, you get zi of 0 equals, so cosine of 0 is 1, so you get zi of 0 equals zi of 0, and sine of 0 is equal to 0, so this term disappears. So we satisfy the first initial condition, that zi of 0 equals zi of 0. If we then take the time derivative of this expression, this will become a negative sine, this will become a cosine, this will multiply here and cancel, and then if we evaluate the derivative, zi at 0, zi dot at 0, this is going to disappear, the derivative of this is going to disappear, and we're going to get zi dot at 0 equals zi dot at 0. So, in fact, this satisfies the initial conditions. The only trouble is that our initial conditions to the physical problem are given in terms of x's, not z's. But we know how x's and z's are related to each other because we know how y and x are related, and we know how z and y are related. So if we work backwards, so in other words, so we need to take the initial conditions given in x's and convert them into initial conditions in z's. And so how do you do that? Well, first you say, well, let's go this way. Okay, so y is equal to m to the 1/2 times x. So I take my initial conditions in x's, I put them in here, I get initial conditions in y. So let's just say we're talking about initial conditions here. So these are evaluated at time 0. And then I have my y, I need to get a z out of it, so I put it into that equation over there. So z at time 0 is equal to q transpose times y at time 0, which is m to the 1/2 x at time 0. Okay? So if I give you these guys, then, and likewise when I take the time derivative, z dot at time 0 is going to be q transpose m to the 1/2 x dot at time 0. So if I give you x at time 0 and x dot at time 0, I can calculate what z at time 0 and z dot at time 0 have to be. So, for example, in this problem, we had m was m, so the square root is just square root of m on the diagonal. the Q transpose is exactly this matrix right here. And so that gives you what the initial conditions are for Z and Z dot in terms of the given quantities. So then you would take those initial conditions that you just calculated and put them in over here. That gives you your solution in terms of what are the components of the vector Z as a function of time. And then after you have the components of the vector Z, at the end of the day, we want to know how X is behaving. So we have to take the vector Z of t and put it back in through sort of the reverse process over here to figure out what X is. So the reverse process, if I tell you, so these statements are actually true not only for the initial time, they're true for all values of time. So let me write it like this. So I've solved for Z. Now I want to know what X is. I have to just invert these guys over here. So if I do that, then I'm going to bring this one over here. So pre-multiply by Q to cancel the Q transpose. Then pre-multiply by m to the negative 1/2 power. So X is going to be m to the negative 1/2 power QZ. So X of t is equal to this. So that's it, and then that's the answer. Okay. So to recap, you have an initial equation like this, and you have initial conditions. The X at time 0 and X dot at time 0 would be given. And you want to ask, how does this system move as time progresses? And the way to find that solution is to introduce two coordinate changes. First, we define y is equal to m to the 1/2 power times x. We substitute that in. We go through these calculations. That basically peels off the m from the front, while keeping the symmetry over here. Okay. Now I'll just point out, you may say, why did you go through all that instead of just pre-multiplying by m inverse? Well, if I took this equation and I pre-multiplied by m inverse, certainly that would remove this, but m inverse k is not symmetric in general. Okay. It is for this particular example because m on the diagonal, but for a more general mass matrix, m inverse k is not symmetric. M is symmetric, k is symmetric, m inverse is symmetric, but m inverse k is not symmetric. Whereas by going through this change of coordinates, this matrix is symmetric for the reason I showed over there with C, A, C, and the transpose rule. So this, we maintain the symmetry of the matrix by doing this coordinate transformation. So A is equal to A transpose. And because it's symmetric, we can then decompose A again into Q lambda Q transpose. And then we do a second change of coordinates over here. And then that completely decouples the system of equations. And we can solve that system of equations if we have initial conditions for the z's. But our original problem has initial conditions for x's, and that's why we have to go through this process to figure out, given initial conditions in x's, what are the initial conditions in the z's. Then when we have those initial conditions in the z's, we solve our problem over here. And then we have a solution in z space, but we really want a solution in x space. So then we have to convert back, given z of t, we need to apply the reverse transformations to get back to the solution that we want, which is x of t. And then we're done. Okay, any questions about that? So easy? Too easy? Okay, so let's see explicitly what does that look like for this example then. maybe let's put some numbers in. Okay, and we'll get a numerical, I mean this is a closed form solution to this mx double dot plus kx equals 0 problem. So suppose that little m is equal to little k is equal to 1. So m over k is equal to 1. And suppose that x at time 0 is the vector 1, 1. So in other words, I have at time 0, I take both masses and I pull them by the same amount and then I let them go. Okay? And let's say that x dot at time 0 is 0, 0. So I pull them, I let them go with initially no speed, and then I watch and see what happens. Okay, so how do we do this? Well, I first need to count. So the first thing that I'm going to calculate is actually in reverse order than the way I presented it. I'm first going to calculate these initial conditions. What is z at time 0? Well, okay, in this problem, because the m is equal to 1, the matrix capital M is the identity matrix, and so I simply get that z0 is going to be q transpose times x0. So what is q transpose? Q transpose is this one over here. It's going to be 1 over square root of 2, 1 over square root of 2, negative 1 over square root of 2, 1 over square root of 2, times 1, 1. So this is M, which is the identity matrix, times Q transpose times X0. That gives me Z0. And this, in fact, is going to be 2 over square root of 2. So it's square root of 2, and then this is going to be 0. So this is my Z0. Z dot at time 0, because X dot at time 0 was the 0 vector, anything times the 0 vector is just the 0 vector. So this is going to be 0, 0. So then my solution is going in Z space, and my lambda 1 here is 1, and my lambda 2 is 3. And so my solution is going to be Z1 of t, just by this formula right here. Z1 of t is going to be the square root of 2 times the cosine of t. And there is no sine term because the z dots are both 0 in this problem. And that's it. So Z1 of t is equal to 2 times cosine of t. Z2 of t is going to be, it's the same, okay, Z2 of t is going to be, well, what is Z2 of t going to be? It's 0, because both Z2 of 0 and Z2 dot of 0 are 0. This is 0, okay? And so this is my solution in Z space, and then I need to convert back, so my Z